Hi, folks. Welcome. Welcome to the Colloquium. I'm sorry about the mask. I'm just getting over a cold. I'm feeling fine. I can see a lot of you are concerned. Uh, um, it's my great pleasure to introduce today's Colloquium speaker, who is our own Paul Romatschke. Paul earned his doctoral degree from the Technical University of Vienna in 2003. Followed by postdoc appointments at Bielefeld University in Germany and the Institute for Nuclear Theory at the University of Washington. He stayed on as a fellow of INT at Washington for a few years before taking a 2-year fellowship at the Frankfurt Institute for Advanced Studies, before joining the CU Physics Department as an assistant professor in 2011. Since he joined our faculty, Paul has been publishing high-profile work on a whole range of diverse topics in theoretical physics, at least to my understanding or my mind, ranging from nuclear collisions and quark-gluon plasmas to quantum gravity to hydrodynamics, including relativistic hydrodynamics at all scales. In fact, he published a book with Cambridge University Press on relativistic fluid dynamics in and out of equilibrium, which will be for sale at the back after the talk. Just kidding. Paul was an Alfred P. Sloan Fellow and also received a DOE Early Career Research Award, supervised a large number of grad students and postdocs in his group, many of whom have gone on to faculty positions or other high-profile scientific careers. Today he'll be speaking to us on the topic of upside-down potentials in quantum mechanics and high-energy physics. Please welcome Paul Romatschke.
Thank you, Tobin. I'm happy to announce that the trip here was uneventful. Okay, so I'll be talking about a topic that is characterized by upside-down potentials, or potentials of endless hills. But before I go into telling you why these potentials are interesting for physics, I wanted to briefly, if I may, show the group members in my group here. So we have Vimal, Seth, Ryan, Willy, and Christian. And I'm happy to announce that Seth today passed his Comms2 exam. Congratulations. Yes. So the idea is now that we sort of venture into these sort of terrains of hills and potentially mountains. But before we do that, I wanted to remind you why we prefer valleys. Okay? Why we prefer valleys? Valleys have some distinct advantages. You can swim in valleys. That's because the water doesn't run down your hill and disappears. You can play golf, and the ball doesn't sort of disappear once you miss the hole or something like that. You can drive cars, although I caution that it's not a good idea, particularly for American drivers, to do that on the shores of Lake Garda. That's not a fun experience. But most importantly, in valleys, you often find pizza, and that's certainly something that you will miss when you're high up on the hill. However, one thing that you might care about is that valleys often also feature nice blackboards, and so we can do physics. So I wanted to get started by showing you a high-energy theorist's version of a valley. Here it is. A valley characterized by sort of a usual-shaped potential. And if we place into this potential a classical ball at rest and let it go, then what will happen is that the ball rolls around in this potential, and it will have an energy that's sort of well-defined and given by this line here. Now, that is nice, but there are some people, notably Niels and Albert here, that might say that, okay, this classical physics intuition is kind of like a little outdated, so we should think instead of a more quantum mechanical version of what the ball's energy can do in this potential. And then you end up with a potential that allows only certain quantized energy levels En, which, of course, many of you have seen ad nauseum, and many of you have suffered through in various forms in these exams. Now, valleys are nice places in both classical and quantum physics. The form of the valley implies that the energy spectra are bounded, meaning that these energy levels, for instance, are bigger than 0, Real values also have the nice property that they lead to real energy, so the imaginary part of the energy is 0, and in real values you often can find pizza, which is of course the main reason for living. Now that we have discussed values, let me now give you a high energy theorist's version of an endless hill. And it looks like this, goes on in all directions. And if we sort of place a ball addressed classically on that potential here, you know what's going to happen. The ball is going to roll down. And we can ask the question what the ball's energy is. I realize that there might be some finals for students going on. So now would be a good time to answer maybe the question. Any student venturing forward, wanting to answer this question? Okay, I have an idea for my final next year. You're no student. It's what? It's constant? What do you mean by that? It's constant, but what value? Well, so if this is 0, this hill sort of goes down all the way to infinity. No, it does not. Well, so this is 0. It goes away all the way to minus infinity. What's the ball's energy? Yeah, it's infinity. So the classical physics ball energy is infinity, and that's sort of what sort of you find in typical classical mechanics. But the sort of upshot of that would be that the endless hill potential makes no sense in classical physics. Okay? But my friends here would all again say, that, okay, that's classical physics. Maybe we should sort of take a more quantum stance at this problem. So in fact, there have been some people who have looked at this. So there's an article by Coleman and Gross entitled The Price of Asymptotic Freedom, where they looked at this. And in that article, they have a statement that says, in the quantum theory, the energy of the system cannot be bounded, and the theory is nonsense. Okay? So that's the sort of end of the statement. And as an aside, I wanted to sort of remind you of different versions of proofs in mathematical physics. So there's a direct proof, where you sort of prove that something is true. There's a proof by mathematical induction. There's a proof by contradiction. There's a computer-assisted proof. And most importantly, there's proof by intimidation. So when I showed you this statement here, that's the entire statement of this paper that says that this quantum theory, the energy cannot be bounded. So what the question for a test would again be, which one of these proofs did this gentleman use in their paper? And I give you a little hint. One of these people happened to be winning a Nobel Prize in 2004. I'll let you mull about this. Okay, it's a take-home final. So the upside down potentials in quantum mechanics is something where there's this claim that this theory is nonsense, but we could also sort of take a non-ideological approach, meaning that we could simply sort of stop talking and just solve the quantum mechanics Schrödinger equation and just see what comes out. Okay? So let's do this. We write down a Schrödinger equation with an upside down potential, minus x to the 4. And we want to solve the Schrödinger equation and find out the potentially quantized energy levels E, subject to boundary conditions that the wave function vanishes at plus or minus infinity. Okay? So simple enough problem. And it turns out you can do this. These are the wave functions. This is the ground state wave function, first excited state, second excited state. Note that they have both real and imaginary parts. And what's shown here is the kind of numerically calculated wave functions and the WKB ones, which are these dashed lines here. So you can see the WKB is a good approximation to most of the energy levels, especially when you sort of go to the higher excited states. Yes? Yeah. If you try to plug in oscillator wave function, yes, that would not be. So basically, sort of, if you want to expand around the classical minimum, there is no such thing. Yes. You can expand this in Gaussians. Yes. You get the same wave functions. This one, yes. It turns out you don't have to. You can solve this on the real axis. This one, yeah. These wave functions die off at infinity. They're normalizable, yes. Ah, then you can't do this. Then you cannot do this. Yes, yes, yes. There's something special about it. Let me just report to you that you could also figure out the energy values. So there's the ground state energy, first excited state, second excited state, and so on and so forth. You can, again, compare to WKB and sort of find nice matching for the higher lying states. And as sort of was pointed out over there, the question is, well, how is this possible? Okay. And the answer, as I sort of have alluded to before, this is possible only in special cases, namely in those where you have a special symmetry protecting you against this sort of infinitely low-lying sort of ground state. Okay? This symmetry is called PT symmetry, standing for parity and time reversal, parity reversal and time reversal. And it was something that was actually sort of discovered a long time ago, back in 1997, by accident, by these two people, Carl Bender and Steve Boettcher, where they looked at the energy levels of a Hamiltonian that's given here. So it's momentum squared minus ix to the n. And they have the energy levels versus n, not necessarily integer, shown in this plot here. And what you find here is that a special case of this Hamiltonian is if n is equal to 4, then you have a minus x to the 4 potential, and you can read off these energy levels over there. Okay? So for special potentials, namely those that are within this class of Hamiltonians governed by this form here, you get real and positive eigenspectra, despite the fact that the system doesn't have a classical one. And that is also to the example that Leo wanted to have. If you wanted to make n is 2, you would get plus x squared, the usual harmonic oscillator. The minus x squared would not be a part of this set of restricted Hamiltonians. Okay, so the statement is that you get real and positive bounded spectra for these Hamiltonians. No, they don't have finite support. No, they go out to infinity, but they die off. It's 1 over x. Yeah, not exponential. Yeah, just 1 over x. In 1D, yes. So, yes. So there are some unusual properties about these wave functions. In particular, the sort of normalization works differently than you would in Hermitian quantum mechanics. Maybe I want to sort of end up with that slide, and then I can maybe sort of answer some of these questions. So for these potentials that I was showing, these are this form here. Note that these Hamiltonians are not even Hermitian. Okay, so there's i's in there, and that means that h dagger is not equal to h. Nevertheless, these Hamiltonians fulfill a specific restricted symmetry, this PT symmetry, which says that as I mirror the sign of space and I sort of take I to minus I, which is kind of like the time reversal in a Schrödinger equation, for those ones, these Hamiltonians sort of map onto themselves. So these are PT symmetric but non-Hermitian Hamiltonians. And the minus x to the 4 is a special case of this system. So for these non-Hermitian Hamiltonians, you get unitary quantum evolutions, but for instance, your probability current that you would sort of write down is typically not real. So they are, yeah. So some of these intuitions that we have from Hermitian quantum mechanics do carry over, like unitarity, but other things do not. But nevertheless, they are solutions to the Schrödinger equation. Yes. 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 Right. It is Hermitian because you don't have, yeah, it's Hermitian, but it's unbounded and it's not part of this special class of Hamiltonian. Okay. So you can do the minus x squared. It's just the analytic continuation of the usual one, and your energy spectrum is Ix, right? Oh, yes. Right, it's Hermitian, but the classical potential is unbounded. So it's a special case that you normally sort of disallow in Hermitian systems. So it's an endless Hill potential, and I'll focus on that. So I'll focus on the properties of this. I will. The reason that I talk about these petit symmetric Hamiltonians is to give you kind of like the broader picture of where this fits in. So that's the debate. Are there any other questions at this point? Yeah. That is a question that I think I cannot answer. It's sort of the idea would be that you try to emulate as much as you would setting up a usual eigenvalue problem in the Schrödinger equation, which usually sort of says that your wave function should die off at infinity, and you just map it over to these petit symmetric ones. If you change the boundary conditions, of course, I guess anything can happen. I can't really comment on that. Other questions? If we finish with the questions early, then I guess I can save myself the rest of the talk. OK, so I wanted to sort of contrast with the standard quantum mechanics treatment, which is built on hermiticity. And we know that hermiticity is sufficient to getting real and bounded ground state energies in particular. But the point that I'm trying to make is that it's not necessary. Okay, so there are weaker conditions that give you bounded spectra, which are not Hermitian. So that's why I sort of wanted to make this example about these non-Hermitian Hamiltonians in the first. So if you have these P2 symmetric potentials, then at least in the class of Hamiltonians that I showed before, you can show mathematically and rigorously that they also lead to real and bounded energy spectra, even if h dagger is not equal to h. And these non-Hermitian systems, we can then sort of go on to show, have unitary time evolution. And that's the case despite not having a classically well-defined ground state.
Sorry,
yes.
The operator.
Yes. The operator X as a potential. Oh, yes. That's right. Yes. So if you have the operator X on an infinite interval, your ground state energy will not be finite. Okay, so you're asking about whether, okay, you're right. So what I thought about was Hermitian operators that kind of also have a notion of positivity. I think I should, that's maybe sort of where the confusion stems from. Okay, yeah. So if you want sort of quadratic forms or something like that. So with this excursion to sort of non-Hermitian P-theories, I want to sort of go back to just Hermitian potentials, but potentially with the wrong side of the curvature. So kind of like these upside down potentials, like in minus x4 potential that I want to sort of use as an example. So if you have your x to the 4 potential, then the solutions to the Schrödinger equation would tell you that the eigenspectrum, lowest lying eigenspectrum, looks like this. There's the ground state energy, first excited state, second excited state, and so on and so forth, despite, again, the fact that this is classically unstable. So now this is something that, in principle, should not be confusing, right? I mean, we have examples of these, like the Coulomb potential, which has a form that sort of also goes to minus infinity close to the origin. So we know that the Coulomb potential, in particular the hydrogen atom, does not have a classically stable ground state, but quantum mechanically that's perfectly fine, right? It was kind of the whole point of quantum mechanics to say that, okay, it doesn't matter that this has no classical ground state. Quantum mechanically, you get a quantized energy level, and we know the ground state energy is this famous minus 13.6 electron volts. Okay? So the point I'm trying to make is that if you have these sort of unusual potentials, it's not sufficient to just use a classical intuition to sort of dismiss certain forms of potential as having no ground state when you talk about quantum mechanical spectra. So of course you might say, okay, that is all sort of calculations, but how do we know that this is really true? Can we test these kinds of things experimentally? And of course, if you think about trying to sort of find tests of these upside down potentials, the first thing that you can come up with is trying to do scattering experiments on like this upside down potential and see what the spectrum sort of looks, the scattering looks. So here we have an animation where you kind of imagine sending in the wave packet to a truncated upside down potential, and you'll see that some part of the wave packet will sort of go through, but another part of the wave packet will sort of reflect. And of course, that's the thing that we expect to happen with a usual scattering experiment. You can also sort of build these things in the lab. So this is an AMO experiment where these kind of scattering experiments have been built. So they use sort of basically engineered quasi one-dimensional potentials in these AMO experiments. Then they send in a cloud of atoms. This cloud of atoms sort of hits the potential, and then there's some part that sort of goes through, and then there's some part that sort of gets reflected, and you can figure out what the reflection and transmission coefficients are, and you can check whether it agrees with the calculation. So generic wave packets scattered onto this upside-down potential will sort of have a certain reflection coefficient, which again you can hope to measure in the lab. However, for these special values, the ones that the solution to the Schrödinger equation says that these are exact eigenspectra or eigenenergies, these wave packets that you sort of send in have precisely the right energy to be a solution of the Schrödinger equation. So the idea would be that that wave packet can just pass through. So these special energies, these E0, E1, E2, E3, and so on, there would be no scattering at all. So this is, yes. 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 No, it's relative to the top. Yes. So for these special energies, you would get what's known or has been termed reflectionless scattering. And the sort of upshot is that, yeah, there's these special potentials where you can send in wave packets with just the right amount of velocity or energy, which will just pass through without reflections at all. You can, again, sort of calculate this through numerically what happens if you have a truncated minus x to the 4 potential. So that's an x to the 4, but it doesn't go out all the way to infinity. That's hard to engineer experimentally. So instead, you sort of have it minus x to the 4 for some width, and then it's sort of constant out front. The eigenenergy changed a little bit because of the truncated nature of this potential, but as long as sort of the width is not very narrow, they're kind of good approximations to the endless Hill potential. And then for those ones, you can look at the reflection coefficients, and you can see that the reflection coefficients go exactly to 0 at some special values of these energies. Okay. So this is something that people are currently sort of engineering. So there's an experiment underway in the Steinberg group at the University of Toronto where they're building this kind of experiment with a truncated minus x to the 4 potential, trying to sort of send in these wave packets and checking whether this idea of reflectionless scattering is actually true. Okay. So you're talking about sort of scattering exactly at the resonance or something like that. It's very similar to that, except that here sort of the idea is that basically your energy levels are above the barrier. So they are not kind of like virtual states or anything like that. They are true sort of solutions to the Schrödinger equation. But otherwise, the idea is exactly the same. Are there other questions? They would be line shaped. Yes, they would be sharp. They're no width. Yes. Yes. So I guess the idea is that you sort of build this up via Fourier modes. So you have different Fourier modes, and if you have sufficient control over at least several of them, you can build this up. But I defer to Ephraim Steinberg's group on how they actually sort of do that in practice. It's in the papers, but yeah. Okay, moving on. I wanted to sort of go on and sort of ask whether, even if this sort of comes out to be true, is there some examples of this non-Hermitian sort of physics that happens sort of outside of designed experiments in the laboratory, if you want? And the example that I want to give is that of QCD in nuclear matter. Okay. The QCD stands for Quantum Chromodynamics, which is the theory of nuclear forces. And it is a theory that has peculiar properties, one of them being that the coupling of QCD, the strong coupling alpha S, depends on the energy such that it is decreasing as a function of increasing energy. So this is a plot from CERN using lab data where they have different measurements of this coupling here for different energies. And what you can see is that there's this trend of the coupling getting smaller as the theory sort of gets larger. The property of decreasing coupling constant in RG speak is called negative beta function. The beta function is simply the derivative of this coupling with respect to the energy scale. And if it's negative, it means that the coupling gets smaller as the energy gets larger. This property of a negative beta function implies a property known as asymptotic freedom, which simply says that if you sort of take this all the way to infinity, so to asymptotically high energies, then the coupling constant will be 0. And that means that you have effectively free theory in the limit of very, very high. So this property of asymptotic freedom for QCD means that quarks and gluons effectively do not interact for asymptotically high energy. And Coleman and Gross, in their paper that I alluded to before, pointed out that only non-abelian fields can have this property of asymptotic freedom. There is a phase diagram associated with quantum chromodynamics. There are people who sort of study different aspects of this phase diagram. We have experimentalists like Jamie Nagel and Dennis, I think, had to leave, who sort of are engaged in collider physics having to do with the relativistic collider, ion collider, and the Large Hadron Collider at high temperature, low baryon density part of this phase diagram. There's also some people in the astrophysics department who are interested in neutron stars, which live in the low temperature, high density regime of the phase diagram. But for us, we are mostly concerned about normal nuclear matter, which is somewhere around here at small temperature, but finite baryon density in the phase diagram. And I wanted to sort of show how this sort of connects to non-Hermitian physics. So as a warning, I wanted to point out that there might be some formulas that people don't like, so caution is warranted. So there's a QCD Lagrangian, which is built out of these quark spinors here. There is a covariant derivative, and we have the gauge covariant field strength tensor F mu for the gluon fields over there. The point that I'm trying to make is that for nuclear matter, there's more matter than antimatter. That's good, because otherwise we wouldn't exist. And that means that this chemical potential mu, which is up here, is bigger than 0. Equilibrium QCD, our main sort of building block to study properties of things like nuclei, is actually sort of provided by lattice QCD, where you take this QCD Lagrangian and you discretize it on a space-time lattice, and then you use computers to sort of simulate the theory and dig out the equilibrium properties of it. The lattice QCD path integral is then defined as an integral over all of these sort of lattice sites of the exponent of the Yang-Mills action, which is sort of this part here, and then the determinant of this fermionic part of it. Okay? So I'm pointing this out because it turns out that for vanishing chemical potential, so remember back at my phase diagram where we don't live, the determinant of this operator is, it's basically real. But for non-vanishing chemical potential, the determinant is complex. Okay? So if you remember back when I sort of talked about complex sort of Hamiltonians, we said that, okay, these are examples of non-Hermitian systems, and because they're non-Hermitian, there's sort of a priori no guarantee that we have ground state energies of the system. So if you sort of go through this, you find that lattice QCD at non-vanishing chemical potential is within that class of generalized non-Hermitian sort of systems. And to be clear, it's not that QCD is non-Hermitian, it's that the lattice QCD version of this, which is our main sort of study of nuclear matter, that's the one that exhibits this non-Hermitian property of the Dirac determinant. So basically, in a nutshell, nuclear matter is essentially non-Hermitian, but it obeys a restricted symmetry, which is similar to this PT symmetry that I had before. So if you use the combined action of charge conjugation C and complex conjugation where you turn I to minus I, you find that the resulting sort of determinant maps onto itself, which means that Ziki symmetry is a property of this nuclear matter at finite baryon density. And because this looks very similar to this PT symmetry, you could sort of imagine that if you were to understand non-Hermitian sort of PT symmetric systems, then this could also sort of help with understanding things like nuclear matter at finite baryon density. So the upshot of this is these activities that I alluded to in the beginning of my talk are actually possible because non-Hermitian quantum field theory has a well-defined ground state. Okay? We are here because that thing exists, not because of some sort of, if you want to, mathematical sort of trickery. Let me now sort of go and try to motivate how to use these upside-down potentials in a slightly different context, in the context of high-energy physics. Unless there's some question. Yes, Leo. Yes. Yes. Euclidean gammas. Euclidean gammas. No. Gamma 0 squared is 1. Yeah. All of the gammas are 1. Psi dagger is psi bar is psi dagger times gamma 0. Yes. But there's the spatial ones are also. Second. Yes. This is Euclidean. Yes. Yes. Yeah. Other question. Yes. Well, if you could do that, then I think that would be a major breakthrough, because then you can actually calculate the ground state energy of these. My understanding is that you cannot do that. Ah, so then you have a sign problem there. Yes. So that will not help either. Right. Right, but if you have to have a real-time Hamiltonian, my suspicion would be that that's not Hermitian either. Okay, we can talk about it. If you have some good ideas, I think that would be interesting. But this I'm certain of, that this theory has a complex Dirac determinant. Because it's a Euclidean gamma matrix. Yes. You take the usual Minkowski version of this, you transform it to Euclidean path integral, and that's where the I comes. I think this, yeah. Yes. Right. I don't Right. So what I'm talking about is that the lattice version of this has on the lattice. Okay, I think we should talk, but for the case of four-dimensional Euclidean QCD, this operator has complex eigenvalues, basically. Yes, that's the same thing, essentially. Yeah. But we should. Okay, good. If you like me to sort of replace the statement that it's non-Hermitian by saying it has a sign problem, these are equivalent statements. That's basically what I'm about. Let me move on. So I wanted to sort of use these ideas of these or these upside down potentials to sort of talk about certain properties of high energy physics. So for the high energy physics standard model, we have heard several talks, several colloquia this semester, where we sort of start out or sometimes show this particle content of what sort of goes into the building blocks of elementary particle physics. And one of the things I want to focus on is the properties of this Higgs boson. Okay? So the Higgs mechanism is a sort of celebrated mechanism where you have the idea that you started with the potential for the Higgs field that kind of like has this Mexican hat shape here, where if you started out with some ball in the middle of this potential, it would roll down, and because it would have to sort of pick a certain location in the sort of round-shaped thing here, it can pick any one of those, but it has to pick one of those, and this property then breaks the symmetry of the potential, which is kind of like the idea behind this Higgs mechanism in high-energy particle physics. So the phenomenon is dubbed spontaneous symmetry breaking, or SSB for short. And a little bit more sort of mathematically, if you start out with the Higgs potential engineered in this form here, where you have a quartic term with a positive coupling and a quadratic term with a negative mass squared, then you can sort of have this sort of shape of this potential where you can imagine that spontaneous symmetry breaking will lead to a mass generation for your part. Now, the thing that I wanted to point out is that because in the standard model, the Higgs field is not living on its own, but it's coupled to other fields in a gauge invariant manner. We have the case that this potential here is actually gauge invariant, meaning that if you rotate this field, complex field phi by complex phase, and simultaneously also change the gauge potential A mu here, then this potential for the Higgs stays invariant. Now, gauge invariance is a local symmetry, and that's important because it means that if you have a local symmetry, there's a theorem that guarantees that you cannot spontaneously break them. Okay, so now, so it's so the proof is on a lattice. That's true. But say again. Yes, it's on a. It's a finite. It's a lattice calculation, but there is you can imagine sort of taking the continuum limit of that. Yes. Right. So I think that it's simpler to understand this statement, right? I mean, phi here is a gauge-dependent quantity, like the gauge potential A mu. And if you calculate the expectation value of a gauge-dependent quantity, you always have to get 0, even in continuum. It's as simple as that. So this sort of property that this local symmetry cannot be broken is something that basically is in direct contradiction with this idea that you have the Higgs mechanism giving mass to the particles by creating a non-vanishing expectation value for this field phi. Okay, so this, so basically this is in direct contradiction to this picture here. So the upshot of this is that the Higgs mass cannot come from spontaneous symmetry breaking. It can sort of look like spontaneous symmetry breaking, but spontaneous symmetry breaking cannot occur for this local symmetry. That's not the only problem with the electroweak sector. There are other problems as well. We have the fact that you can't really sort of get a non-vanishing vacuum expectation value because of gauge invariance. There seems to be no deep reason, I think, for the fact that there is this tachyonic mass term in the Higgs potential. So you can write that down, and it does its job. But why would it sort of have this property that is basically a tachyonic mass term? There is experimental data from LHC fit to these weak coupling perturbative calculations that kind of say that the vacuum that we're in is basically a metastable vacuum. So that we are stuck in a metastable state, and there is a true ground state somewhere out there that has lower free energy that we are not in. But of course, that is kind of a very strange proposition, given that we believe that in the early universe, the theory or the universe was much hotter, so thermal fluctuations were much larger, which means that there's essentially no way you can get stuck in a local false minimum if in the early universe you basically were exploring all of phase space. Okay. Finally, there's a hierarchy problem, meaning that the Higgs mass that sort of comes out from the model is essentially a tree level, and then you get sort of radiative corrections. But in the sort of standard model perturbative treatment, the radiative corrections are basically controlled by the size of the cutoff scale that you put in there, which typically is very large. So you would expect, in principle, radiative corrections to give large correction to the Higgs mass, but the experimental sort of value is around the electroweak scale, which is much smaller than this cutoff scale, which is known as the hierarchy problem. Okay. So I would say that there's something fishy going on with this standard model of particle physics. There's sort of several problems, none of them which I think cannot be sort of solved by other means, but taken as a whole sort of seem to give the impression that there might be something missing, or there might be a better way of sort of doing it. Okay. So this is why I wanted to advertise a potential way out of this, which is using these upside-down potentials to solve not one, but several of these problems of the electroweak. So let's go climbing hills. But a warning, we might have some technical terrain ahead, so I will again sort of resort to some mathematics to do that. I want to talk about quantum field theory for a scalar field phi. Think of this as being the Higgs field, and it's defined in terms of this path integral, where we have a Euclidean action that has sort of a usual form here with a quartic term, in principle with a coupling constant lambda here that we start out thinking positive. And the main ingredient here is that you don't have one, but you have many components of this field here, which will be something that will allow us to do calculations in regimes that are not weak coupling. So this model is known as the ON model, has been around for a long time. And the main thing that I wanted to point out is that for n is 4, which are 4 real components of this field, this corresponds to the standard model Higgs field, which is 2 components of a complex scalar field. Okay, so now that I have written down the model, let me sort of state that if you use this number n and make it very, very large, you can use 1 over n to be a small parameter that is independent of the coupling, and you can use this to solve the theory order by order in 1 over n, which is independent of basically a weak coupling expansion, which sort of gives you a different tool to explore it. So this is fully non-perturbative. It's not a weak coupling expansion. The main physics ingredient that is new to quantum field theory, that's not present in sort of quantum mechanics or quantum even quantum field theory in lower dimensions, is that you have infinities everywhere. Okay? So this is a famous property of quantum field theory, and it requires the use of renormalization, meaning that you sort of have a consistent way of subtracting infinities and make the remainder sort of finite. As a consequence of that, you find that the coupling constant is actually not a constant, but it depends on the scale, similar to the coupling of QCD that I showed at the beginning of. So for the ON model, you can actually sort of do this. You can sort of renormalize the theory non-perturbatively. And what you find is that this coupling constant is sort of given by this simple formula here, the leading order in large n. It's just a logarithm with a different scale. And we can look at the plot of this coupling constant, or coupling without constant. Kind of looks like this. So for low energy scales Q, the coupling is small and increasing. And then at a certain scale, which is 1 in this unit here, it sort of dips, comes down to minus infinity, and sort of increases back to 0 from below. And the main point that I will emphasize, or two main points I will emphasize, is that A, this is something that comes out as a non-perturbative, not weak coupling sort of result in a consistent 1ON expansion. And the other thing is that as you sort of go to high energies here, you always have the coupling being below 0, which means that the coupling that's relevant at like UV scale of this theory is negative. So effectively, the potential for this scalar field theory is an endless Hill potential. Okay? So it just comes out from the math. There's really not much you can do. Also, this is not a new discovery. This is something that was known basically for decades. For scalars, this beta function is always positive. Okay, it always rises. But there's this non-analytic behavior at this particular scale that comes out of the renormalization equation. So the absolute value of the running coupling actually decreases because you go back to 0 at very, very high energy scale. So what that implies is that the math says that this scalar field theory is actually asymptotically free. The coupling goes to 0 for very high energies. So remember that this is the famous plot for quantum chromodynamics, where the coupling decreases as a function of energy scale. And the prediction from this mathematics is that for Higgs physics or scalar field theory, the coupling at very high energies should exactly behave the same way. It should basically become smaller as you sort of go to higher and higher energies. That's not the way that Higgs physics is usually done in textbook high energy physics. Okay, it's cut off at lower energies before it even sort of gets negative. But if you sort of take the consequence of the mathematics, this is basically what you would expect for the Higgs coupling to do at very high energies. Now, if you sort of take this model and then couple it to sort of gauge fields the way that you would with the standard model Higgs, you can sort of see what happens with basically the different components of the standard model. So the point that I'm making is that it's the same Lagrangian as the standard model, but under quotes solved better by using this 1ON expansion rather than the sort of weak coupling expansion. It's just a different way to solving it, but maybe we sort of can discover some different physics. The main point that I'll emphasize is that there are additional experimentally testable predictions that come out doing the calculation this way. So again, this is the Lagrangian of the model. I will not bore you with the details. The main point is that you do this non-perturbative expansion in 1ON. What you find is that you have a Higgs mass and a gauge boson mass, which are entirely due to radiative corrections. If you remember back, one of the problems that I identified were the radiative corrections in the standard model treatment. Here, these radiative corrections are necessary for you to give mass to the gauge bosons. There are no tachyonic mass terms. There is no VAF, so this naturally sort of is consistent with Elitzur's theorem. It is asymptotically free, and because the radiative corrections give you the Higgs mass, there's essentially no hierarchy problem. It doesn't solve the hierarchy problem, it just evades it because it never has a cutoff scale in this whole construction. Yes. That scale is set, this scale is the renormalization scale of the electroweak interactions. It's dynamically generated from the radiative corrections, just like lambda QCD in quantum chromodynamics. So it comes out from the math. It's lambda ms bar. You can, yeah, it's one scale that is sort of coming out of the calculation. One of the things that comes out of this calculation is that there are two vacua or saddle points. One of them is the perturbative saddle, which you find to be unstable. It's a disfavored vacuum state. And there's a non-perturbative saddle which is unconditionally stable at large n. This is very much reminiscent of this situation where in the standard model we have the statement that we are stuck in an unstable vacuum state and there's some true vacuum at some other sort of configuration. Here you can identify both of these, finding the perturbative saddle and the non-perturbative saddle. And the additional prediction is that there should be a Higgs-Higgs bound state with a mass of around 250 GeV that comes out of this calculation. OK. I know that I'm out of time, so I will go quickly and tell you a little bit about the reactions of the community. And I guess you have sort of seen some of that already in this room. OK, so I'm afraid to tell you that the reactions, as far as my statistics goes, kind of cluster with age. There are some exceptions to the rule, but sort of the 100 or so data points that I have kind of fall into this diagram here. And there's a kind of like hard phase transition somewhere around 55-ish, I would say. People below the age of 55 generally are kind of enthusiastic about this. They sort of are positive, whereas the slightly older generation kind of like are very skeptic. And that's fine. It's just what you sort of find. It turns out that these sort of hard line also correlates with some other qualifiers. So for the early age faculty, postdocs, and students, these can all be found in this part of the phase diagram, whereas Nobel laureates, breakthrough prize winners, and journal editors can be sort of found to the right. Okay, and I want to sort of hark back on particularly the journal editors. So I wanted to tell you about my experience trying to publish with the Journal of High Energy Physics. So I submitted one of these manuscripts to Journal of High Energy Physics. The editor assigns a referee. The referee sort of says that it looks fine, publish after minor correction. So I do minor corrections, I send it back in. And the editor assigns a different referee. The referee B says, it's OK, but you really need to fix this, that, and A and C. And so publish after major revisions. So I send in major revisions, submit it back to JHAP. The editor assigns a third referee. The third referee says reject. I said, OK, well, this is weird. I appealed to the editor saying, OK, every A sort of said minor revisions, so what are we doing now? And the editor rejects the appeal, and that's the end of the story. However, I didn't give up on this. I sort of sent it to a different journal. The different journal, the two reports came back. They were kind of positive. And not only that, the sort of journal editor said, OK, we really want to highlight your work. Would you be fine with us highlighting it at the cover page of our sort of volume? I said, fine, I'll do that. This is what it looked like. The cover page of the Applied Math Journal. This was the paper, Life at the Landau Pole. This was my AI-generated picture of this. So I was very happy. So I told a colleague of mine, look, it worked out. I sort of published and sort of did all this stuff. And she said, what kind of publishing company is it? And I said, MTBI. And she said, oh, they publish absolutely everything. It's OK. So I thought this is kind of unfair, right? I think it's a reasonable paper. But after this sort of experience, I thought, OK, what do I have to do in order to sort of get some of this work published in the Journal of High Energy Physics? So I mulled about it for some time. So I want to publish a paper about upside-down potentials, inverted potentials in JHAP. What kind of key work do I have to include to get a slightly better positioned editor to sort of review this? And I tried the following thing. I put out-of-time ordered correlators in the title. And it worked. So this got published in JHAP. Look, I sent it in September 16. It was published or accepted September 25. It was published October 17. So I think that the key is just to sort of use the right tactics. So it's very hard to swim against the current, which is something that CU students know from the very beginning because they are sent this letter here. And I think this is some advice to sort of heed for the future. So I'll sort of be careful to sort of be within the herd and sort of not try to swim against the current. And that's all I had to say. Thank you for your patience. And I'll be hopefully sort of climbing more hills because I think the views from those are beautiful. Thank you so much.
Thanks. There have been a number of questions already, but we have time for some more. I'm going to try to prioritize people who haven't asked anything yet.
Hi, thanks for the nice talk. So you mentioned in your model for sort of a better version of the Higgs model, you get the Higgs mass and the gauge boson masses, but another important part of the electroweak model is the top quark mass. What about that?
Yes. So clearly, well, so there are two things here. First of all, whether trying to set up something like electroweak theory qualitatively can be done within these upside down potentials. I think that what we have is kind of like a proof in principle that this works out. The second question is whether the numbers come out right such to describe experiment. This is clearly something we have to work out. We haven't included the fermions yet, so I can't really tell you whether we get top quark mass the way that we should, but clearly it's something we need to check before sort of saying that this is a competitor to the Higgs mechanism or something like this. At the moment, it's just conceptual, if you want. It's manpower limit. Yeah.
Okay, so I want to come back to the question of gauge invariance of the Higgs field. What gauge invariance does is to change the vacuum. So in other words, gauge invariance tells us that there is an equivalence class of vacua. But once you pick a point on that equivalence class, the point for an infinite volume theory, you cannot change it by any local process.
You're
That's
saying
the
that if you
usual
pick
argument.
a gauge,
So I don't see what's wrong with that.
you're saying if you pick a gauge,
You pick a point on that equivalence class of vector.
which is picking a
right?
gauge.
You take a U1 gauge theory. You
Yes.
have a circle, right?
This one.
Right.
This is
so you
U1
have a
gauge.
circle of vacua.
Yes.
Right. So that's an equivalence class of vacua. You
Yes.
pick one point on that. I'm talking about the valley around the hill. Okay. Take
Yes.
one point on that, but no local. Yeah. Take one point like where the ball is.
Yeah.
There is no local process which can change that. And that's the usual argument. I think it's probably in Weinberg's book or somewhere.
I don't dispute that. The point is that if you pick one point on this circle, you have
Yes.
effectively broken gauge invariance.
Well, yes, of course. But you are
Yeah, if
picking
you
a
break
point.
gauge invariance, then it's no longer gauge invariant. That's right.
So what? You are choosing a point. Your gauge invariance tells you that you have a whole equivalence class. So I don't see the problem with that.
But well, so let's take a different one. It's the same sort of example, but it's the gauge potential, right? So if you were to try to evaluate the expectation value of a gauge potential, what do you think you get?
That's not relevant here because we have this is now when you do that and include the gauge field is massive now, right? It's the W and Z bosons.
This is a U1 gauge theory. There are no W's. So this is just
so
the
this
so I
photon
think
gets a mass.
I think I understand what you're saying, but I think my point is that if you don't break the gauge and you just ask about what's the expectation value of gauge-dependent quantities, then the usual answer is 0. It has to be 0.
Well,
That's this statement, okay?
yes, but that's not relevant for the Higgs physics.
I don't understand why it's not relevant. It's supposed to be a gauge
Because
theory.
you have picked a point on that value.
I think I understand.
That's where-
if you
that's
break
where we are
gauge
supposed
invariance,
to
then
live,
yes, you've
so-
broken it, so you've picked a point. Yes, that's right. But I think if you see it from the point of view of what kind of the expectation value of certain operators should look like, then if you hedge an unbroken gauge symmetry, you expect there to be no vacuum expectation value.
All right, we're running pretty late. I think I'm going to just let one more question come in, and then if you want to harass Paul afterwards, please please come down and do that.
Yeah. So I guess I haven't been following particle physics as much. So you mentioned that there's a strong indication that it's not in the true vacuum.
Yes.
So can you say a little bit more about that? What is that evidence and how strong is it? Because that
Yes.
seems like a big issue, sort of regardless of the rest of the talk. Just as sort of an
Yes.
issue for the current theory.
That is true. So what I'm referring to is precision electroweak fits to LHC data. You sort of do your fits, and you've discovered that at, I forget, I think it's 95% confidence level, or maybe 97% confidence level, the parameters that you parameters that you get for your model indicate that you have either metastability or completely unstable vacuum for our present universe. I can give you the reference, but yeah, I think this is well known in particle physics. We have my particle physics. Is what? Yes. Well, it's theory. It's theory fit. It's theory fit to experimental data. Yeah.
All right. Thank you very much for the great questions, great discussion, and great talk. Thank Paul Romatschke.
That's fine.